So, say you're feeling particularly nonconformist in math class one day and decide you want to unleash your inner geometry rebel. With such a mindset, Euclid's postulates seem like a great place to start. So, you're reading along, straight lines, right angles, the usual, until you get to the fifth postulate, reading, given any straight line and a point not on it, there exists one and only one straight line which passes through the point and never intersects the first line. Undoubtedly the clunkiest and most unnatural of the five, the parallel postulate stands out as a natural target. You begin to wonder if you can deduce the fifth postulate from the four simpler ones, so you try that for a while but soon abandon the effort, and with good reason too, because mathematicians had tried to do just that for over 2,000 years, but to no avail. Instead, you decide that it might be more fun to just modify the parallel postulate to your liking, so you cross out the 1 and replace it with a 0. The idea that all lines must intersect goes against your Euclidean inclination, but you spot a globe nearby on your desk and notice that the lines appear parallel at the equator, but intersect at the poles. Curiously enough, when you try and draw a triangle, the angles add up to more than pi. In fact, if you were standing on the equator, made a pi-halves turn and walked to the North Pole, made another pi-halves turn, walked back to the equator, and returned to your starting point, you would have traced out a triangle with 3 right angles. What you've stumbled upon happens to be spherical geometry, a space with constant positive curvature, as opposed to a flat plane which has 0 curvature. Setting this aside for the moment, you return again to the parallel postulate and decide that instead of 0, you want to know what happens if you tried to have it read, given any straight line and a point not on it, there exists an infinite number of straight lines which pass through that point and never intersect the first line. Even weirder, in this new curvy space, you find that the angles of a triangle add up to less than pi. This second non-Euclidean space is called hyperbolic geometry, a space with constant negative curvature. Thinking about what happened to triangles and the 2 new types of space you seem to have discovered, you start thinking about angles, so naturally your brain wanders to tiling. You remember from boring Euclidean geometry that you can fill a plane by tiling 6 triangles around a vertex, and wonder what you'd have to do to turn a flat space into these newly discovered spherical and hyperbolic worlds. Compared to a normal plane, the spherical plane seems to curve inwards, so you wonder what would happen if you removed some triangles so that there were only 5 around a vertex. Sure enough, the resulting tessellation seems to imitate a sphere. Conversely, the hyperbolic plane appears to fan outwards, so you try taking the flat plane and adding more triangles until there are 7 around each vertex. Indeed, any tiling where the angles around one vertex add up to more than 2 pi results in a model of a hyperbolic plane. Examining the hyperbolic tessellations, you notice that the plane grows exponentially dense as you move further and further away from the center. In the visual representations that have been squished into Euclidean space, you have to draw the tiles smaller and smaller to make room for all of them, but in reality all the tiles are congruent. Here, in this hyperbolic tessellation of 3 heptagons to a vertex, you see that all of the heptagons are indeed the same size. You imagine extending the plane outwards with more and more heptagons, and you see its beautifully hyperbolic nature, how it gets crowded and chaotic, curling up on itself and simply unable to fit into the confines of Euclidean space. Your thoughts wander back to Euclid, and you can't help but feel a deep sense of awe when you think about how 5 postulates led to the birth of everything we know and call Euclidean geometry, and how a simple tweak causes our well-developed notions to fall apart. All you can do is wonder what might have happened if Euclid had just done a thing or two differently.